last talk in this morning session. The third talk will be the foundation model for domain generalization in CPAS, computational pathology, which is given by Joona Pohjonen from University of Helsinki, who is a PhD student at the Helsinki Urological Cancer Research Group, University of Helsinki. He obtained a Master of Science from the University of Helsinki and a Bachelor of Engineering from Metropolia. Joona's field of interest is robustness analysis of deep learning models in computational pathology.
I try it now.
Okay, Joona.
Okay, yeah, now again.
Okay.
Just a sec. Oh. Okay, can you see my screen?
Sure.
The presentation is showing, not the empty Safari window. Yeah, okay, so hi, so I'm Joona Pohjonen, and my talk today is going to be named Embrace Consistency over Performance. And this is actually a combination of, two talks I've given before. Do I have a laser pointer? No. Augment Like There's No Tomorrow, where I talk about the role of augmentation and building consistent neural networks, and then HistoEncoder, where we build a foundation model for digital pathology and how these intertwine. So the contents of my talk are going to be how to evaluate models. So how can we prove that our models work, and during training, how can we see what is wrong with the models, and then how can we train consistently performing models. So, and then I'll talk a bit about how to train foundation models if we have time for that. But yeah, so let's start by asking what is required from a neural network intended for clinical use. So it would be nice to have 99% accuracy, or maybe like better than human performance. It should be extensively externally validated, or then like the model should be explainable. All of these are important. Can you see me?
I can see you, but it's still on the first slide, so we can't see your first slide if you're still on it.
Okay, let me share again. Let's try this one.
Okay, yeah.
Now you can see contents. Ah, okay.
Yeah.
So quickly, first talking about evaluating models, then how to train them, and then a bit about foundation models if we have time. So yeah, what is required from a neural network? Good accuracy, extensive validation, explainability, everything is important, but the most important thing is if the model's good enough, it's good enough as long as it's consistent. So if the model performs consistently despite different data sets, then like that's good. Like even if the accuracy is that good, we can factor that in if it's consistent. So we know when it makes mistakes and what's the probability of making a mistake. So let's talk a bit about how to evaluate models. So we have a hospital here and then an external data set, and a lot is happening between that line. We have to prepare the samples, stain them, then scan them, and then pre-process the files and everything until we get the actual external data set. And we can denote this line as an unknown data generation process. So there's a lot happening in that line. Can you see me? Yeah, everything's good.
I think good.
Okay. Yeah, so a lot is happening in that line, and it's inherently unknown because there's so much stuff happening. So next we take our external data set and we evaluate our fancy neural network, and two things can happen. Either we succeed or we fail. And if we succeed, maybe the external data set had the same biases as our like training data set. Maybe if we used a different scanner, it might have not succeed. Another data set might differ. So we don't really get that much out of success on external data sets because we don't know if it has the same biases. And also when it fails, we know that something is wrong, but we have no idea what, because the data generation process is unknown. And this is like the most important thing in my presentation that I want to emphasize, that external data sets cannot be used to establish clinical usefulness, robustness, or generalization ability, because the data generation process is unknown. Only thing we can actually get from this is that we know if it doesn't work, but in the end, we don't know why it doesn't work. But what if we could have a known data generation function? And that's where distribution shifted data sets come in. So we take the external data set and apply a known distribution shift function denoted by F over all the images to create a new data set. And now any difference in performance between the external data set and the distribution shifted data set is completely defined by the function F. So this means that if we take the distribution shifted data set and evaluate our fancy neural network, then when it succeeds, we know that the model is invariant to the distribution shift F. So the model works despite the distribution shift. And the same is true if the model fails. So we know then that the model is fragile to that distribution shift function F. And this was a lot to take in. So let's take a really simple example. So here we have an external data set. And we'll generate a distribution shifted data set from that external data set by blurring all the images in the external data set. So now the blur function is going to be our distribution shift function. So now we can take both of those data sets and evaluate our fancy neural network. And we see that the AUC is 97. So that's perfect. We can publish in Nature. That's perfect. And then we take the distribution shifted data set and we see that the accuracy drops significantly. So our model does not handle blurry images. Even though you can still see like all the cells and everything in this image, the model like has no idea what's happening. So now, because we used a known distribution shift function, we know exactly what the problem is. If the model sees blurry images, we can go back and fix it. So we go back, do some machine learning magic, and create a fancier neural network. Then we evaluate again with the external data set, and we see AUC is 95. It's not as good. We might not publish in Nature, maybe in Science. And then we evaluate the distribution shifted data set, and we get an AUC of 94. So the performance is now consistent despite the fact that we blurred all the images. So now we know that our model is robust to blurriness. And if someone gives me these results, I can also say, okay, I can see like your model handles blurry images well, because you can show that it's consistent despite the distribution shift. So this was all like made up figures and everything. So let's take a real world example. So here we have an external data set. And here I have one state-of-the-art model that I trained to predict prostate cancer from whole slide images. And the values here are AUC multiplied by 100 to make the figures nicer. So no, it's 95. Again, we can publish in Science. That's good. Next, we generate distribution shifted data sets from the external data set by adjusting the hematoxylin and eosin staining intensities. So you can see here that each tile represents a data set, and then the y-axis denotes the hematoxylin intensity, and the x-axis the eosin intensity. And now when we evaluate the state-of-the-art model, we see that this happens. So this is not good. Like even small changes to the staining intensities render the model basically useless. So you can see here that even a small shift in the hematoxylin intensity like significantly drops the performance. And for most of these images, like it just has no idea what's happening. So how can we improve this? So first thing I did was I read this paper, gradient starvation. It has like a simple penalizer that you add to your raw network outputs. So one line of code, and then it's mathematically proven to increase the robustness of distribution shifts to your model to distribution shifts. And you can see that it helps a bit. Like here, like it increases the AUC by 20 percentage points. So that's really good, but still like, this is not what we want. We want this to be more robust. I would like the model to perform consistently for all of those images. So next I thought like maybe augmentation might help. So what is augmentation? First, it's a way to generate new training samples. So we have an original image, then we take a transformation function, here randomly resized crops, and you create augmented images. So if your data set is small, you can generate, make your data set bigger by generating new augmented images from your original data. And this has been kind of a traditional view of augmentation and what most of the augmentation methods are based on, generating new training samples. There's also a better view that's like currently more viewed. Augmentation is more viewed now as a way to tell the model to ignore certain things. So the example below is actually an example of how to introduce scale invariance to your model. So the randomly resized crops tells the model to ignore scale differences. So it doesn't matter what the actual size of the cells are, like it doesn't matter because like scale invariance isn't built into neural networks, like not convolutional transformations, like transformers. It says like you have to include it by transformations. And the traditional view kind of emphasizes more light augmentation because we would like the new samples to be as close to the original as possible because we're generating new samples that might have come from our data set. So then light augmentation makes sense. And then strong augmentation is kind of for the ignore part because we would like the samples to be as far away as possible while still remaining in the same label. So let's open up this argument a bit. So as far away as possible. So here we have a space of all possible images. Let's add a few images there. So now we have a few dogs and a few cats here. So now we train our neural network and we get this decision boundary denoted by blue. So now we evaluate the model with a new sample and we notice that it goes outside the decision boundary. So this is a false negative. And when we use augmentation, we can like expand, like sample the space around dogs more efficiently because these images are also dogs, even though they look kind of weird because we augmented them, but they're still dogs. So you can like sample the space more efficiently with strong augmentation. And this is exactly what we would like here. Like you can see the decision boundary is kind of like on the diagonal line. And then like we would like it to sample also the images on the edges. So how can we do that? So automatic augmentation is kind of the way to go. So there's two things to automatic augmentation. First is an augmentation space. So we have to choose transformations and then magnitudes for those transformations. So here's an example. Saturation is a transformation, and then you can see the magnitude range for that transformations below. And then the second thing is how can we sample the transformations and the magnitudes from the augmentation space? So random augment was kind of the first like clever or good automatic augmentation strategy, which had two hyperparameters. So the number of operations and then a fixed magnitude. Operations is usually set to 2 and magnitude is like 17 out of 30 or something. But the fixed magnitude is not good for sampling because we're taking step always to the same direction. So a random step, but always in the same direction. So that's not good. So then came trivial augment, which is currently the state of the art in automatic augmentation. And it uses a uniform magnitude. So it randomly selects something here uniformly. So it samples the space better, but it's only taking a single step because it's one operation. So it's taking like a random step, not randomly walking the sample space. So that's where I started. I wanted to create a strong augmentation method that actually samples the space more efficiently. So for augmentations, I basically chose all of them. So all of the fast ones. And for example, this here, this isn't the stain intensity changing shift because it's really computationally intensive and I work with foundation models. So I didn't want this to become a bottleneck. So tone shift isn't that, it's kind of similar, but still not. But then the ranges I want it to be as wide as possible because I want to sample as far as I can. And then how I sample them. So magnitude uniformly, something from the magnitude range. And then operations, I'm using a multinomial probability distribution for the operations. So the random it's like randomly walks the augmentation space or the sample space compared to a random step as it was with trivial augment. So yeah, this was a lot. When I did build this, I didn't train any neural networks because I didn't want strong augmentation. Like the method to be overfitted to any data set. Only thing I did was I had a picture of a dog, and when I couldn't see the dog, then I stopped. So here you can see images from Strong Augment, and all of you, I think you can see the dog. Maybe not this, you can see it on my laptop, but probably not on the screen. It's really dark, but still, these are all dogs, even though they're augmented like really strongly. And now I like, this is what oh, this is missing one slide. Well, okay, that's fine. This is also, you can think of this as IHC stains. So most of the people, when I present this, they say, what about IHC stains or something where the color actually matters? Well, when you use, for example, hue transformation for IHC stain images, the color changes are still there. It just changes what the colors are. The actual like underlying distributions is still same. The positive cells are still different from the negative cells. So like, I'll talk a bit more about like how this kind of work, because like, let's first see if it works. So we had this distribution shifted data sets with stain intensities, and this was our state of the art with which didn't work. And this was now the trivial augment method. And does strong augment work? Well, yes. So now only thing I changed in the augmentation method is that I sampled the space of possible images more efficiently around the samples. You can see that the model performs consistently despite any changes to the hematoxylin and eosin stain intensities. And I want to emphasize now that the transformations like used to create the distribution shifted datasets aren't included in the augmentation space. So it's still performing well. And we can include those H&E stain intensity variations to the augmentation method. And that has already been done a few years ago by Gerd Litjen's group. And it was called Random Augment H&E. And you can see that that also works. Like when you include the specific explicit transformations, like it does work, but you can still see that strong augment is better. Like even though this includes this transformation. So yeah, this is all simulation. What about real life? So we had in the paper, we have a clinical validation where we have 3 prostate samples, and those then we used 3 different glass types, scan everything with 2 different scanners, and this is all being done in 4 different medical centers. So this gives us 72 validation cases, and we'll focus only on 1. So these images now are the same prostate sample, so serial sections from the same prostate sample, same glass type, same scanner. Only thing that's different is a different medical center. So you can immediately see that the stainings are a bit different. So when we evaluate the methods on the image on the left, you can see that all of them perform similarly. Like random augment is a bit worse, but still like I'd like count this as a like win. I don't care if it's 99 or 94, it's still good. Like that's fine. And then when we evaluate the method on the second one, this happens, and this is unacceptable. Like these models should perform similarly on this second image, but there's a significant drop in performance. And this random augment HE actually includes the H&E staining transformations in the augmentation space, but it still doesn't work. And why is that? It's because it's not enough to only include a transformation to your augmentation space. So here's an example of a transformation called Solarize, which is included in strong augment, random augment, trivial augment, and you can see the images here. And here's an AUC value for the distribution shifted datasets. And you can see that strong augment performs consistently, but even though the Solarize is included in random augment, trivial augment, it doesn't help. Like it's not enough to include the transformation. So why does it work? Let's take a few, like small sidebar to stain normalization. So a really common method is to like how to train neural networks is to like normalize the H&E stains before feeding the images to a neural network. So you have dirty samples which go into a normalizer, which can be Mashenko or like some kind of algorithm to do the stain normalization, or then a separate neural network that cleans the samples. And then only the clean samples are fed to the fancy neural network. And what I wanted to do with strong augmentation is to force the neural network to normalize the samples. So it get like the dirty samples go into strong augment and it creates filthy samples. So really hard samples that in order for the neural network to learn the task, it has to first learn how to normalize the images. And my kind of like idea behind this was that if they're filthy enough, it's easier for the model to learn to normalize than like memorize all the different augmentations. And this is kind of like this block, I thought like maybe the neural network learns how to do reverse augmentation. And kind of the results in our paper kind of suggest that this is the case because it does work even for transformations that aren't included in the augmentation space. So this is still speculation. I don't explicitly enforce the normalization to happen. So I don't have a loss function to normalize this, but it's like, it seems to happen in the network. So let's explicitly enforce the normalization. But I didn't want to do it for classification models because they're not that nice. I wanted to do this for foundation models. So quick sidebar, what is a foundation model? There's two steps for foundation models. There's a pre-training step and then an adaptation step. So during pre-training, the foundation model centralizes information from vast amounts of data using self-supervised learning. And then anyone can take that foundation model and easily adapt it to their downstream task. And this step is kind of like, I handle this. And then the adaptation step is only thing that anyone else has to care about. And what I asked myself is, what is a good foundation model? Well, a good foundation model for me is that I could also skip this. Like, I don't want to train the foundation model or fine tune it at all. All I want to do is like, I want to extract features from the foundation model and then use only those features. So we can take the extracted features and use those for downstream tasks. So you can leave the foundation model as it is, and you don't have to train that again because they might be really big models. So for that to work, it has to be, the features has to be useful and they have to be consistent despite changes from a different medical center to center. And this here can be easily enforced during pre-training. So I can augment the samples really strongly and then enforce that for all of those samples, the feature that comes out is the same feature, despite the unmeaningful differences in the images. So let's first see if the features are useful. Here we have the foundation model and we extract features. And when you look at the UMAP of the features that I extract, this is only for epithelium tissue in prostate. So you can see here that the benign clusters nicely separately, and then all the cancerous epithelium clusters together. And you can even rediscover the Gleason grading system for prostate cancer in this UMAP. And because they like similar histological patterns cluster together, if we cluster those features, we can annotate slides automatically by visualizing the clusters on a slide. And this requires no training. That's perfect. So the features are useful. Are they consistent? So one way we can like see this, like UMAPs aren't good here because UMAPs are kind of cheated. What we can do is we can fit a KNN classifier from the extracted features. Then we get a new data set from another like hospital or medical center, and then we extract features also from that, and then take the fitted KNN classifier and predict with the features. And now, if the features map in separate places in the feature space, the KNN classifier wouldn't work anymore. But if they're close together in the feature space, despite the differences between medical centers, the KNN classifier should work. And I'm sorry for the next slide, there's a lot of stuff here, but here you can see my histoencoder foundation models here on the top. And these, this is now results from KNN classifier fitted with tile images from Karolinska, which is from Sweden, and then Peso and Radboud are from Netherlands, and Helsinki 30 and 60 are datasets from Finland. And you can see that the KNN classifier works perfectly despite the images coming from different medical centers. And here I compared commonly used neural networks pre-trained on ImageNet. And you can see here, like the most important part is this Helsinki 60. So it's clear that when using ImageNet pre-trained models, the images from Karolinska map into a separate place in the feature space. And that's why it's just like randomly guessing labels, the K-mean classifier. So yeah. Then finally, does self-supervised learning help with domain generalization? I don't have time to talk about that. Go read this paper. It's really good. It does help. And they also provide foundation models for digital pathology in this paper. I did ask for them like access to those models 2 months ago, but I still haven't heard back. So just remember that. But maybe in like future, it's more readily available. But yeah, that let's conclude. So in the beginning, I had 2 questions: how to evaluate neural networks and how can we train neural networks? So you can use shifted data sets to prove that your network actually works. And they're also useful during model training because you like if the model doesn't work, you know what's wrong and you can go back and fix it. And then during training, you can use strong augmentation to help your network perform more consistently. And then that's not like strong augmentation isn't the band-aid that fixes everything. You just still use state normalization. And then now the specialized transformations. So the strong augmentation transformations now are really generalizable. It would be beneficial to add more specialized transformations for digital pathology. For example, air bubbles or pen markings or like random artifacts that can be usually found from the digital pathology slides. And then also like strong augmentation helps you focus, like when you collect a data set, you don't have to focus that much on collecting like samples from different scanners, like all the different scanners. You can more focus on biological diversity because strong augmentation helps you ignore the differences that scanners bring to the table. And then finally, like raise a flag feature is something that's like any model that goes to clinical practice should have. So if the sample is truly out of distribution, the model should raise a flag and say, hey, I don't know what this is, but please have a human look at this image. So yeah, that was everything. Thank you. And here's links to the preprint and then the GitHubs for strong augmentation. And then if you want to use the foundation models, they're also readily available from my GitHub. So thank you.
Thank you, Joona, for the great talk. I think we have a time for a couple of questions. Any questions from the audience, please send them. Yep.
Hi, can you hear me?
Yeah.
Can you hear me now?
Yeah, kind of.
Thank you. Thank you for the talk. So I had one question on the history encoder that you talked about. Did you actually compare with the same architecture that you self-supervised trained with ImageNet self-supervised training, or was it only fully supervised?
Sorry, I didn't quite get that. Did you ask about like, did I compare to ImageNet or?
Sorry.
It's kind of echoey.
Sorry, then,
Hard to hear.
Is it better now? Just trying it.
is that any better?
Do you want to come
No. Sorry.
No, it's not your fault.
Okay, now I can hear.
Yeah, sorry, the mic wasn't working. Yeah, and I just had a question on the table where you compare with all of your models with ImageNet with your histoencoder.
Yeah.
This one. Did you compare your self-supervised trained one with self-supervised trained ImageNet models or not?
Yeah, I actually took them out of this table because there was too much stuff. But that like it increases because supervised training is not good for generating useful features. So self-supervised trained on ImageNet, the same models, the same training setup, it was around 75, 80, the AUC from all of these. So it was better, but then like not that good.
Yeah, exactly. It was interesting, just more like that's more of a fair comparison compared to what you did. So it's just
Yeah.
All right, thank you.
Any other questions?
Just gone.
Okay.
But thank you very much, Joona, for the really interesting talk. I
Thanks.
really agree with you. Data augmentation can help a lot in lots of applications that you're doing. So my question is that how necessary do you think data augmentation is when you have access to enough data? So my personal experience is with mitosis detection, for example, when I use my data set, when I use a really effective, even specially designed pre-training algorithm, self-supervised algorithm to pre-train my algorithm on a lot of unlabeled data set, and then use it for mitosis detection. It performed good if I don't provide it with enough data, but if I train the model on whole mito data set, for example, it actually outperforms that. So do you think it's still necessary to use this kind of pre-training or self-supervised training on unlabeled data sets when we have access to good amount of data for training?
Well, it always depends on your task. Like if you have enough data, I would still like use kind of strong augmentation, but it wouldn't have to be that strong. Like, I don't know, like if I go back a bit, like this, like when you use strong augmentation, like you can think this as a dartboard. So you're trying to hit the middle part. And then when you use stronger augmentation, you make it a bit bigger. And this is actually a bad example because usually this doesn't happen. Because now you can see here that light augmentation, the AUC is 95, and strong augmentation improves that AUC. Usually what happens is when you use strong augmentation, the AUC actually drops a bit. So you might get like 92 AUC, but then it's consistent over this area. So it depends on your task. If you can handle all the normalization and all the scanners that you use for the neural network, if you can provide it with clean enough samples, then I would probably use lighter augmentation to increase the network performance. If you get what I'm talking about.
Yeah, I meant more about starting the training from ImageNet rather than using pre-trained on labeled data sets. So using augmentation all the time, of course. But
yeah, okay.
If you have enough data, you might not need to pre-train. I mean, it would be really nice to investigate this more often to see how does it work. But anyway, thank you very much.
Yeah, no worries. And I can still say, like, if I understood correctly, for like the presentation I gave in Budapest like a month ago, there I talk more about the foundation models, and there you like the fine-tuning part is necessary for ImageNet pre-trained models, but not for like foundation models with domain-specific pre-training. So then the model actually knows how to see, and then you can only use the features. But then if you use ImageNet, then like always you have to fine-tune.
All right.
Yeah.
Thank you very much. Fantastic.
Thank you, thank you, Garen. Okay, this is the end of the first session. We're gonna have the next session at 11:30. Thank you, everyone.